And lots of examples in this section on the method of partial fractions. And so we start off by saying this was the nicest case, and we kept messing with us a little bit. So we said, okay, we start off with 2 factors, and we said we could have 3 factors or more. We also looked to see what happens if we had repeated linear factors, and we had ways to take care of that. In the last video, we just saw a way to take care of how of the case where the degree of the numerator is not less than the degree of the denominator, and we do that using long division. And so there's one more thing we have to look at, which is what happens if the denominator doesn't factor into linear factors. And so here's the problem we're going to be looking at, where our denominator factors into a linear factor times a quadratic factor, and this x squared plus 9, this is an irreducible quadratic factor. We can't factor any more. If you try to solve x squared plus 9 is equal to 0, you try to find roots of that to factor it, you'd see that you get imaginary roots, so we can't factor this. So how we're going to handle this is that, once again, we are going to find a partial fractions decomposition. And in each one of these cases, it's going to look a little bit different. And so the target that we're aiming for is a constant over x minus 1. That shouldn't surprise us. And then for the x squared plus 9 term, the upstairs is going to be of the form bx plus c. So whenever you have this case, a linear factor times an irreducible quadratic factor, this is what we are aiming for. A over the linear factor plus bx plus c over that irreducible quadratic factor. And so just as before, our goal is we have to figure out what A, B, and C are. Our first step is to cross multiply, clear out everything. So on the left we have 10, and we'd have A times x minus 1 and x minus 1 cancel, so A times x squared plus 9, plus bx plus c. The x squared plus 9's cancel, so plus bx plus c times x minus 1. Okay, so now, as I said, we have to find what A, B, and C are. We've done this plenty of times before. I'm going to do this one by expanding out the right side and comparing coefficients of different powers of x. So when we expand this out, we get ax squared plus 9a plus multiplying this out gives us bx squared plus cx minus bx minus c. I'm going to group this. I'm going to group these by what is the coefficient of x squared? It's a plus b. And what's the coefficient x here? That is c minus b. And what is the constant term here? The constant term is 9a minus c. Okay, so let's go to a new slide here. Let me recopy that. 10 is equal to a plus b times x squared plus c minus b times x plus 9a minus c. And now let me make a little change here on the left to underscore what we're about to do. This isn't just 10. This is 0x squared plus 0x plus 10. And in order for this to be true for all values of x, the coefficients of each power of x have to be the same on both sides of these equations. So for x squared, on the left, that's a 0. And on the right, that's a plus b. For the power x, that is just x. On the left, that is 0. And on the right, that is c minus b. And then finally, for the constant term, that's x to the 0, we have 10 on the left, and on the right, we have 9a minus c. So now we have this system of equations that we want to solve for a, b, and c. And some of these can go very quickly. So this one, 0 is equal to c minus b, this tells us b and c are exactly the same. A plus b is equal to 0. This tells us a is equal to minus b. And because b and c are the same, a is equal to minus c. And so then down here, looking at 10 is equal to 9a minus c. So if a is equal to minus c, c is equal to negative a. And so we have 10 is equal to 9a minus a. So 10 is equal to 10a. A is equal to 1. And if a is equal to 1, that forces b and c to both be negative 1. So what is our partial fractions decomposition? 10 over x minus 1 times x squared plus 9 is equal to 1 over x minus 1 plus bx plus c. So that is minus x minus 1 over x squared plus 9. If you don't believe us, you can always check this by combining this together. You know, all of these partial fractions decompositions, we should never make mistakes on them because we can always combine these together, put it over a common denominator, and if we get 10, great. If not, we know something's gone wrong here. So, okay, what do we have to do here for a final integral? So this is going to be the integral of 1 over x minus 1 plus minus x minus 1 over x squared plus 9 dx. I'm going to break this up as 3 separate integrals. The integral of 1 over x minus 1 dx, then minus the integral of x over x squared plus 9 dx, and then minus the integral of 1 over x squared plus 9 dx. And so let's revisit the sheet here of these facts to use. So this case is this case here, so that's easy. This one is this case here. We're just going to do it by substitution. Substitute in u is equal to x squared plus 9 will give you this. And then this one is an arctangent here. So you can do that from the arctangent formulas. So when we use all of the appropriate formulas, natural log of the absolute value of x minus 1 minus 1/2 natural log of absolute value x squared plus 9. We don't need the absolute value there because x squared plus 9 is never negative. And this is minus 1/3 times arctangent of x over 3 and then plus c. So that's how you do this kind of problem when you have an irreducible quadratic factor. And so to have you practice with this, I want you to evaluate this integral, the integral of 3x squared minus x over x plus 3 times x squared plus 1. So there's an irreducible quadratic factor, so you want to set it up in the way that we just did for this problem.